Welcome to part 4B of the particle physics videos that I'm recording for AQA Particle Physics. I've called it part B because we'll have covered some of the conservation rules in class, and I'll have provided PDFs of those slides for you to look through. You should definitely have a read through those and check that you are comfortable before we move on with part 4B, which is mostly about the property of strangeness, not discussed in class. So this is where the names go from difficult to just plain silly. So just to revise what we did in class, you might be asked to show that a decay is possible, and what we mean by that is show that the quantum properties remain the same before and after, and we use the technical term conserved to remain the same is what we mean. And we see lots of layouts for how students go about showing conserved properties in a decay such as this one, what we might call beta positive decay. My advice is stick with the one that we give you in class. As a marker, I've seen multiple approaches to showing this, and many of them I don't credit with the marks because it's so difficult to follow when you're staring at them on a screen. So maybe pause the video, think about which properties you would conserve here. I'll give you a clue. Baryon number is definitely one, and then pause the video and have a go at this question before we move on. Okay, hopefully you're back with us having had a go at this. I can't recommend enough actually trying the questions. So what am I showing the examiner? That the charge before is +1, and that afterwards there are 3 particles, 2 of which have 0 charge and 1 has a charge of +1. So then to the right of that, I'm explicitly stating +1 equals +1, and therefore charge Q is conserved. We can do the same for baryon number. We can do the same for electron-lepton number. And remember, I've really tried from the very start to get you to think about lepton number as 2 different properties. One for the first generation, the electrons, one for the second generation. And do go back and look at your notes if that isn't clear, or come and ask me. Right, so most properties are always conserved. So they're easy, and you should just learn these. These should be ready to go, because if you get a question on them, it's a gift. So charge, baryon number, electron and muon lepton numbers, momentum, and mass energy are all conserved. Note that I haven't taught you about mass energy yet, and that will be coming in section 5 of this course. Strangeness is a property of strange quarks. And in our course, the only thing that has strangeness are strange quarks. We don't see any other fundamental particles with strangeness. Remember, we've ignored 3 of the quarks that exist. Now, strangeness is always conserved when strange particles are created. And they're created, you must know this, by the strong force. And what that's saying in reality is just that we create a strange anti-strange pair, because the anti-strange quark will have the opposite strangeness to the strange quark. So overall, there is no net change in the strangeness of the universe. But when strange particles decay, they can decay in such a form that strangeness is not conserved. And this decay occurs by the weak force. So we've got strange particles created by the strong force in pairs, which means the strangeness is conserved. Strange particles decaying on their own by the weak force, meaning strangeness is not necessarily conserved. Right. Strangeness is clearly a silly name. It was an expression of the fact that the first particles we found with strangeness behaved in a way that was totally unexpected. So people expressed that as them behaving strangely, and unfortunately the name stuck. On top of the silly name, the other annoying naming convention is that the strangeness of the real strange quark is -1, whereas for everything else, we've tended to make the real version plus. Okay, so you need to remember that a strange quark has strangeness -1, whereas an anti-strange quark will therefore have strangeness +1. And really, from your point of view, it's just a property. I know we give it a number and people call these quantum numbers, but it is a property. Things with that number behave in a certain way, and we just need to keep track of that. So a typical question might be, based on what I've just told you, a K plus kaon, which you should already know, kaons are mesons, and they are mesons with strangeness. Decays into a pi plus and a pi naught. And you should already know that they are mesons with zero strangeness. Explain one property which is conserved and one property is not. Pause the video here and have a think. If you've needed to flick back, that's fine and great. Conserved, you could have said charge. There's +1 before, +1 afterwards. You could have said momentum. Lepton number wouldn't really be ideal because there's no leptons here. So whether you might get a mark for that in an exam is dubious. But you could pick a number of different properties. Not conserved, there's only one, strangeness. Okay, the K plus is strange and the two daughter particles are not. Therefore, strangeness is not conserved. It must, and for later, it must therefore be a weak interaction. So based on what I just said, they often ask the question the other way round. Right? So you get an equation given and say, is this a strong or a weak interaction? Or which interaction would be responsible for this decay? And if you look at the decay and you say, well, the kaon, so meson with strangeness, but afterwards we've got two leptons, neither of which have strangeness. Therefore, strangeness is not conserved, and the logical step is therefore it must be a weak interaction, because it's only in the weak interaction that strange particles decay and strangeness is not conserved. And the spec is very clear on this. Strangeness can change by 0, +1 or -1 in weak interaction. There's now a few slides on just some miscellaneous items that you should know as part of the course. So there's a throwaway line in the spec that says the proton is the only stable baryon into which all other baryons decay. Now that might seem very strange because we've previously told you things like carbon-12 are hugely stable. They've got half-lives of inordinately long periods and they've got neutrons in them. So how can they possibly be, these neutrons be unstable? Well, what we're saying is that baryons that are left floating in space on their own decay into protons, not baryons that are stabilized in nuclei. Okay. So if I fire a neutron through space, it's got a half-life of about 10 minutes. It will decay, or half of 100 neutrons fired, 50 of them would decay in 10 minutes. Once a neutron is in the nucleus, that stabilizes it. And we will talk about that, but in detail, not really until year 13. But you should know. And it's tested in a very unimaginative way. So this is, I've seen this question numerous times in the last 10 years on the AQA spec. You either know it or you don't. If you know it, it's a very easy and quick mark. Some other bits, so the black writing is stolen straight from the spec. The kaon as a particle that can decay into pions. Well, you know, I'm sure you're thinking to yourself, kaons, mesons with strangeness, and pions, mesons with no strangeness. So I'm hoping, but pause the video if you need to think about it, you can tell me straight away which interaction this is. It's a weak interaction. Now, just a health warning, it doesn't say the particle, that the kaon always decays into pions, just that it can. Right. Equally, it says the muon is a particle that decays into an electron. So if the muon lepton number is always conserved, when a muon decays, we can't lose the muonness of the universe. So we're going to have to create something. And again, pause the video if you're not sure. They're the answers. That is the end of this part 4B, a very short video this week because you've got quite a large number of questions to do for homework as well. I would remind you that there'll be a test on this material straight after half term, and it's best learnt as you go along. Probably expecting 2 to 3 hours work per week out of you as a minimum, with a bit of independent study maybe on top of that. Some of you might feel that's a lot. I guarantee you'll thank me if you keep that up through the 2 years when it comes to the exams.